Visit https://www.pythonhomeworkhelp.com/https://www.pythonhomeworkhelp.com. Email support@pythonhomeworkhelp.com, support@pythonhomeworkhelp.com, or call us at +1 678 648 4277. One difference equation system 1. Consider the system represented by the following difference equation, where xth n and yn represent the n samples of the input and output signals, respectively. 1.1 poles determine the poles of this system. Number of poles, 2. List of poles, 3 and -1/2. 1.2 behavior. Does the unit sample response of the system converge or diverge as n infinity? Converge or diverge? Diverge. Briefly explain. System 2. Consider a different system that can be described by a difference equation of the form y n equals x n plus I n minus 1 plus by n minus 2, where a and b are real-valued constants. The system is known to have two poles, given by 1/2 plus or minus j 1/3. 1.3 coefficients determine a and b. A equals 1, b equals -13/36. 1.4 behavior. Does the unit sample response of the system converge or diverge as n infinity? Converge or diverge? Converge. Briefly explain. Two geometry OOPs. We will develop some classes and methods to represent polygons. They will build on the following class for representing points. Class point, def_init_self x, y self.x equals x self.y equals y. Def distance to self, p return math.sqrt, self.x p.x, * 2 plus, self, yp.y, * 2, def_str_, self return point plus str, self.x, self.y, _repr__ equals _str__. 2.1 Polygon class. Define a class for a polygon, which is defined by a list of point instances, its vertices. You should define the following methods. __init__ takes a list of the points of the polygon, in a counterclockwise order around the polygon, as input perimeter, takes no arguments and returns the perimeter of the polygon. P equals polygon, point 0, 0, point 1, 0, point 1, 1, point 0, 1, p dot perimeter 4.0. Class polygon, def__init__, self, p self dot points equals p def perimeter, self p equals self dot points n equals len p per equals 0 for I in range, n per plus equals p I dot distance to p I plus 1 % n return per. 2.2 Rectangles. Define a rectangle class, which is a subclass of the polygon class, for an axis-aligned rectangle which is defined by a center point, a width, measured along x-axis, and a height, measured along y-axis. S equals rectangle, point 0.5, 1.0, 1, 2. This has a result that is equivalent to S equals polygon, point 0, 0, point 1, 0, point 1, 2, point 0, 2. Define the rectangle class, write as little new code as possible. Class rectangle, polygon def__init__, self, pc, w, h points equals, point, pc.x w/2.0, pc.yh/2.0, point, pc.x plus w/2.0, pc.yh/2.0, point, pc.x plus w/2.0, pc.y plus h/2.0, point, pc.xw/2.0, pc.y plus h/2.0, polygon__init__, self, points.
2.3 Edges.
Computing the perimeter and other algorithms can be conveniently organized by iterating over the edges of a polygon. So, we can describe the polygon in terms of edges, as defined in the following class. Class edge, def__init__, self, P1, P2 self dot P1 equals P1 self dot P2 equals P2 def length, self return self dot P1 dot distance to, self dot P2. Def determinant, self return self dot P1 dot X asterisk self dot P2 dot Y self dot P1 Y asterisk self dot P2 dot X def underscore underscore str underscore underscore, self return edge plus str, self dot P1, self dot P2, underscore underscore repr underscore underscore equals underscore underscore str underscore underscore. Assume that the underscore underscore init underscore underscore method for the polygon class initializes the attribute edges to be a list of edge instances for the polygon, as well as initializing the points. Define a new method, SumForEdges, for the polygon class that takes a procedure as an argument, which applies the procedure to each edge and returns the sum of the results. The example below simply returns the number of edges in the polygon. P equals polygon, 0.00, 0.20, 0.21, 0.01, P dot SumForEdges, lambda E, 1. Def SumForEdges, self, F return sum, F, E, for E in self dot edges. 2.4 area. A very cool algorithm for computing the area of an arbitrary polygon hinges on the fact that the area of a planar non-self intersection polygon with vertices x0, y0, xn, yn is, where M denotes the determinant of a matrix defined in the 2 by 2 case as. Note that the determinant method has already been implemented in the edge class. Use the SumForEdges method and any other methods in the edge class to implement an area method for the polygon class. Def area, self return 0.5 asterisk self dot SumForEdges, edge dot determinant. Or def area, self return 0.5 asterisk self dot SumForEdges, lambda E, E dot determinant. Or def aux, E return E dot determinant, def area, self return 0.5 asterisk self dot SumForEdges, aux. 3 signals in systems. Consider the system described by the following difference equation: y n equals x n plus y n minus 1 plus 2y n minus 2. 3.1 Unit step response. Assume that the system starts at rest and that the input x n is the unit step signal u n. Find y, 4, and enter its value in the box below. Y, 4, equals 21. We can solve the difference equation by iterating, as shown in the following table. X n y n minus 1 y n minus 2 y n 0 1 0 0 1 1 1 1 0 2 2 1 2 1 5 3 1 5 2 10 4 1 10 5 21. 3.2 block diagrams the system that is represented by the following difference equation: y n equals x n plus y n minus 1 plus 2y n minus 2 can also be represented by the block diagram below, left. It is possible to choose coefficients for the block diagram on the right so that the systems represented by the left and right block diagrams are equivalent. 1 Enter values of P0, P1, A, and B that will make the systems equivalent in the boxes below. P0 equals 2A equals 2/3, P1 equals minus 1, B equals 1/3. For the left diagram, y equals x plus ry plus 2r 2y, so the system function is. For the right diagram, the two systems are equivalent if equating denominators, P0 P1 equals minus 2 and P0 plus P1 equals 1, i.e., P0 equals 2 and P1 equals minus 1. Equating numerators, A plus B equals 1 and P1 A plus P0 B equals 0, i.e., A equals 2/3 and B equals 1/3. For Robot SM. In Design Lab 2, we developed a state machine for getting the robot to follow boundaries. Here, we will develop a systematic approach for specifying such state machines. We start by defining a procedure called IntClassifier, which takes an input of type io.sensorInput and classifies it as one of a small number of input types that can then be used to make decisions about what the robot should do next. Recall that instances of the class io.sensorInput have 2 attributes: sonars, which is a list of 8 sonar readings, and odometry, which is an instance of utility pose, which is attributes x, y, and theta. Here is a simple example. Def IntClassifier, imp if imp.sonars, 3, less than 0.5, return front wall L if imp.sonars, 7, less than 0.5, return